Now, a common problem in double integration is we want to find the area of a region. So we can use Green's theorem to translate this into a line integral around the boundary of the region, not he region. So the area of D would just be the double integral with respect to D of dA. But we know, using Green's theorem, that it's equal to the boundary of D of x dy, right? Thinking of it from one perspective, because we'd have that one D, and just like that. But we could also do it the other way and get the partial, the integral over the boundary of D, y dx, right? So how could we simplify this? We subtract these, and we get 1/2 the line integral over the boundary of D, x dy minus y dx, right? Because if these are equal, we can obviously show this equality. So sometimes we come across regions with holes in them, or annuli, as an example. And a fair question to ask would be if Green's theorem can help us deal with these. Let's look at some regions. So first, let's think of a domain to kind of get us into the thought process of this, of a domain as we normally might look at it. But here's a crucial difference. We're going to split it right here and have a D1 and a D2. Well, let's create boundaries of D1 and D2. Well, we have this curve here, which we'll call C1, like that. And then we'll have a C2, which will be right here, which also would go this way. And then, finally, we'll have C3 be this middle line. Well, if I follow this one, if I want to keep the orientation, I have to go this way. But if I want to follow this orientation to create a boundary, I have to go this way, right? Which maybe I should label this one as pink. So that way we follow that there, and this one as blue. Okay. So now let's do our integral here. Well, we can split up the integral in terms of D1 and D2. So we have the integral of D1 of the same sort of thing. Now I can break it up as the integral C1 of P dx plus Q dy plus C3 P dx plus Q dy, right? But then this is only that part, so I'm going up C3, which we're going to think of this way as C3. That's why it's that way. Now here, similarly, we'd have integral of C2 P dx plus Q dy plus the integral of, now if I'm going to set my C3 to be going like this, then we would be going along the negative of C3. P dx plus Q dy. Now, here's the trick. The negative, right, of the line integral along the negative path is the same as going on the positive path and switching this integral to a negative. Now we see cancellation here. We can cross out this integral, and we should get what we expected, right, from Green's theorem, as if we didn't break it apart. So let's look at our next region and put a hole in it. So now we have this region D. How are we going to integrate this region? Well, first of all, let's kind of do what we might think of and break it into non-holy pieces. So we put a line here and a line here, and we have a deformed Pokeball, but we can call this region D1 and this region D2. Okay? Now, in order to have our orientation, let's make this line C1, this line C2, C3, C4. Not the explosive, just the line. So, positive orientation, we follow here, here, here. Ah, we forgot about a spot. So let's call this C5 and this C6, right? So we go around here, we go to here, and then we're back up here. All right? Now similarly, for D2, we'd go here, 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 and now we're going the negative of C4. And we go down this way. And then cross like this, which is the negative, and then back down like that. Lots of arrows. So let's actually do our integral. Well, we've got over D of blah, 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 dA equals, I'm just going to put a box here. You guys can fill it in. D1, blah, 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 dA plus D2, blah, 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 dA. And let's break it up into our parts. And we are going to get the integral of C1 of P dx plus Q dy plus C3 of P dx Q dy, which I'm just going to call that from now on M, because I can do that. Let M equal P dx plus Q dy. Mathematicians are lazy, so I don't like writing all those things. M plus, all right, C5 plus C4. And we got our M's here. Then we need to do D2, so we get plus, all right, C2, M plus, well, as we know, it's now minus, from our previous example, minus C4, M, minus, no, actually we're positive here, so plus C6, M, then minus C3, M. And that means we get some nice cancellation. So we have C3, nope, C3's, whoops, this should be a C2. I don't know if I said it accidentally wrong. My bad. So our C4s cancel, and our C3s cancel. So, to make this easier, let's think of this whole thing to be C. So if I followed all this around, this to be C, kind of pointing there. So C1 plus C2, I have, this is equal to integral, the closed integral of C, all right? And M, that's right, that's what we were calling it. Plus, now we have the integral of C5 M plus the integral of c6 m. Now, why didn't I just name this one differently? Now remember here, right, we need, in order to do this circle around and find the closed curve, we need positive orientation. Now currently we have it circling like this. Is that positive orientation? No. You need to go this way around the curve. So therefore, we need to flip it. And we'll call this now C prime, but instead we're going like this around the curve in the proper orientation. So this whole thing should be equal to C m minus C prime m, which kind of makes sense. We do the integral of the whole of the outside minus the integral of the inside, which is kind of what was going on here. This kind of method should work for your other types of integrals. So I would maybe create a interesting situation, maybe two holes or something like that, or odd situation, and see if you can kind of piece together to get used to orientation and how to add and subtract these integrals in terms of their boundaries.